I'll begin with a word of prayer. Heavenly Father, we thank you for this day. I thank you for these students. I just ask that you just bless this class, help us to understand what we need to about one-to-one and inverse functions, and just pray that you be glorified in what we do, Lord. In your name I pray. Amen. Okay, so I started the other section here with a question, but I'll start you guys with a definition. One-to-one function. So here's the definition. If f of x1 equals to f of x2 implies that x1 equals to x2 for all x1 and x2 in the domain of f, all right, then f is 1 to 1. A logically equivalent thing to notice is that if there exists x1 not equal to x2 for which f of x1 is equal to f of x2, then f is not 1 to 1. All right. Now, so we had various things we could say about a function before, right? Like the big one was the graph of a function. If you have a graph, right, it's only going to be the graph of a function if what's true. It has to do what? It has to pass the vertical line test, right? So is there something like that here? What would be a graphical? What would it mean graphically for a function to be 1 to 1, right? Or what would it mean for the function not to be 1 to 1, graphically speaking? So let me lead off with that example here. If we had a function, right? And this really isn't so much an example as it is a theorem I'm sharing with you guys. But if I had a function that looked, I don't know, like this, right? Here's my graph, y equals to f of x. And then I can ask the question, is this function 1 to 1? All right? And so you can see graphically that it's not by looking at the following horizontal line. Check this out. So if I take this horizontal line, like here, right, this horizontal line intersects the graph two places, here and here, right? So think of this as being x1, and think of this over here as being x2, right? But what do you, if there's a horizontal line that intersects, they're both on the same y value, right? So we have x1 not equal to x2, yet f of x1 is equal to f of x2, right? So this function, it fails what's known as the horizontal line test. So what does the horizontal line test say? The horizontal line test says the function is 1 to 1, all right, if every possible horizontal line that you can draw only hits the graph at most 1 point. If you hit at 2 or more points, that means that there are two different values for the function which both output the same value. And so a 1 to 1 function takes one value to one value, right? And that one value it maps to is only mapped to by that input x. There's no way you can have two different x's which map to the same y for a 1 to 1 function. All right? So that's one way you could test for a function be 1 to 1 is graphically. If you can draw the graph, you could look for the horizontal line test. If it fails the horizontal line test, not 1 to 1. All right? Another way we can do it is algebraically. So algebraically, decide if f of x equals to x squared plus 3 is 1 to 1. Now, of course, we could use the graphical method again, but I want us to use the algebraic method. What's the algebraic method? So you can use, listen, like, so when I do the algebraic method, I don't like to use x1 and x2 because x1 and x2 are not, they're kind of annoying for algebra, right? So logically speaking, we don't have to use the letters x1 and x2 up here, right? You can replace this logically with just f of big A equals to f of big B implies A equals to B. So I will use that as my sort of default notation here to decide algebraically if the function's 1 to 1. Is rather than using x1 and x2, because then I'd have to write x1 and x2 a bunch of places, and I think we'll do better if we write A and B. All right, so here we go. So you've got f of A is equal to f of B. All right, so we assume this. Now our goal is to either prove or disprove that A has to be equal to B. Now the thing is, the only solution we can get is A equal to B. If we get more than that, it's not 1 to 1. So here we go. This is what A squared plus 3 equals to B squared plus 3. Can you solve that? In other words, can you find A as it relates to B? Can you simplify this equation? I think we can. Subtract 3 from both sides, right? And if you want, we can move everything to one side. I mean, we could do it like this. A squared minus B squared equals to 0, right? And then you can factor. You have A plus B, A minus B equals to 0. And so how can you get the product of those two things be 0? There are two things, right? Either you have A equals to minus B, or you have A equals to B, right? In summary, you get A is plus or minus B. So what does that show us? That shows us that this function is not 1 to 1. It's not 1 to 1 because we set f of A equal to f of B and we worked the algebra out. We didn't get A equals to B. Okay? Is this surprising? I would say it's not surprising. We could graph this function, right? What's the graph of this function look like? Yeah, parabola opens up, y-intercept is 3, right? Does this function pass the horizontal line test? Most assuredly not, right? Because if you just take any horizontal line, like up here, you're going to hit this and this, right? And so like what's going on is you could think of this as being the A, and what's the B? B is minus A, right? So the value of the function is the same at any input, and it's negative. So it's not 1 to 1. Are we good? All right, so let's do one that's a little bit. Well, I think that's enough. So this is the concept of 1 to 1. A 1 to 1 function is a function. Well, I guess I should give you an example of one that is 1 to 1, right? Let's try that out. My bad. Example 3. Let's look at. I don't know, f of x equal to 3x plus 7. Is this function 1 to 1? I mean, it better be 1 to 1. I said I wanted to give you a positive example, right? So we can either do graphically or algebraically. Which do you guys want to do? And I'll speak at once. Both? I'll take your both and trade it for algebraic. Okay, so f of A equals to f of B. So we get 3a plus 7 equals to 3b plus 7. Subtract 7 from both sides, you have what? 3a equals to 3b. Lo and behold, a equals b. So through straightforward algebraic steps, we can see from assuming f of a is equal to f of b, we get a equals to b. So this function is 1 to 1. And somebody said graph it, fine. We can graph this. This is easy, right? What is this? Yeah, y-intercept 7, slope 3, so it's basically something like this, right? And if you're looking at horizontal lines, how many points do those intersect that line in? Just the one, right? Aw, man. I thought I had it. Are we good? Oh, here's a harder question. Can you guys tell me, how could we modify the first two examples I had to make it 1 to 1? Like, what if you had control of the function? Like, how could you modify these examples so that the given function becomes 1 to 1? What could you do to change what we were given? I mean, by default, whenever you write a formula, our greedy assumption is that the domain is all possible x that it makes sense for, right? So our assumption here is that the domain of this one is everything, right? And it's kind of ambiguous because I introduced this other function graphically, but the domain of this one would also be assumed to be everything, right? What if you could trade your domain for a new domain which wasn't so big? Could you make the domain smaller so that the new function with smaller domain, which is called a restriction, could you restrict these functions to a smaller domain which would make the function 1 to 1? Let's just focus on example 2. Can you restrict, let's say g of x, so call it example 4 here. Let g of x, same formula, x squared plus 3, for x, how about this, greater than or equal to 0. So let's define the domain of g to just be positive, or rather non-negative numbers, right? So the domain of g equals 0 to infinity. See if we do that. If we make that modification, is the new function 1 to 1? Check it out. What's the graph of g? What's the graph of g look like? It's the same as the graph of example 2, right? What's the difference? Yeah, it's just on the right side. So you just got this piece, right? That's the graph, y equals g of x. Does that pass the horizontal line test? It surely does, right? But the algebra looks the same, right? What's the difference? Notice that the algebra said that the trouble was from having the value in its negative, right? If you go through this algebra, same algebra, right? For the example 4, when you get to the step a equals minus b or a equals b, you don't, that doesn't do anything for g because g doesn't contain both a and b that are negatives of each other in the domain, right? So because of how you've restricted the domain here, the troublesome solution from the algebra is ruled out. All right? So this is a generally difficult question. And when I teach calculus, I tend to review this in the pre-calculus part of calculus like the first week. And I will tell you, most students can't understand it. This idea of restricting a function to make a smaller function which is 1 to 1. I just did it. You saw me do it. It didn't seem like it was a big deal. But if I ask you to do it, bad things will happen. I know. I've tried it before. So I probably won't test you on this, but I want you to be aware of this idea, okay? So mostly I'm just going to give you functions and ask you, are they 1 to 1 or not, all right? So this creative extra step I just made is something I was sharing with you, but I probably won't require of you. Now, if you go on, once you're a math major, you need to learn this. This idea of restricting a function is an important idea. All right, so let's go on. Let's see here. I guess I can write for here. So definition. Let's talk about inverse functions. So let me just draw a picture to get us started. So maybe you've got a function that goes from a set U over to a set V. All right? So the function goes like this. So what I'm saying is that the domain of f is U, the range of f is V. All right? And f takes us from a point x in U typically to a point we call y over in V, right? Now, what would f inverse do? See, if you think a function as something that maps x to here over to y over here, right? If I want to talk about an inverse, what's it going to do? It's going to go the other way, right? It's going to go the other way. And so the inverse function we can think of as going backwards, like this. All right? And in order for this to make sense, in order for the inverse function to actually be a function, it turns out logically we must insist that the function we're inverting is 1-to-1. If the function is not 1-to-1, that's why I'm talking about 1-to-1, because in order to invert a function, we need this 1-to-1 property to invert it. So here's the definition. You know, f from U to V, a 1-to-1 function has inverse function f inverse from V to U defined as follows. So I'm going to give you a kind of greedy definition. There's really two equations that it has to I mean, well, fine. Minimally speaking, you could say this: if y is equal to f of x, then x is equal to f inverse of y. That's the deal. The inverse function, if the function maps x to y, the inverse function maps y to x. There's really, I sometimes give this as the definition. I tend to prefer, and you know, there are people who are more logically efficient than I am here, of course, but the two things I always try to write for students are these. Number one, f inverse, let's say, of f of x is equal to x again. So what I'm saying is that the function, the inverse function, undoes what the function does, right? And this is for all x in the domain of f. Sorry, I used the funny looking E here. This just means element of, right? For all x in the domain. Number two, f of f inverse, and I'm going to use a different letter here, y, is equal to y for all y in range of f. So the inputs to the inverse function are the outputs for the function, all right? And the outputs for the function are the inputs for the inverse function. I think I said the same thing twice, but let me just write it up here. There's the domain of f is U, but the range of f inverse is U, and the domain of f inverse is V. In other words, what I'm saying is just this. I'm saying that, oh well. It's okay. I should hang this thing out to dry. So maybe I can wring a little bit more out of it. I should have brought a towel, like a paper towel or something, because if you can wipe the water off the board, it works better. At some point, this shirt has to be washed, though. Given the amount of teaching I'm doing this semester, I feel like the shirt has done well to make it this far without being washed. All right, so.
Is that good coffee?
Yeah, pretty good. Who's to say it's coffee? This is a mug that was custom made for me by my online boss. I teach an online class, and the chair of the online math, she makes these mugs for different people. This is my mug. It's a wonderful mug. It has slightly larger volume than Dr. Putney's, which means I'm more important. But Dr. Putney's mug is also nice. Dr. Sprano chose a very small mug. He could have had this mug, but Dr. Sprano chose a much smaller mug, and which just makes Dr. Sprano look more like more of a giant when he holds it. So, because Dr. Sprano is also, he's, I don't know, what is he, 6'4" or something, and he definitely could have been a football player. Okay, so where was I? Okay, so let me talk to you about then how to find the formula. How to find formula for F inverse. All right, so here's step number one, right? Y equals to f of x. All right, so I'm assuming for the purposes of this current discussion that we're given the formula for the function. We're trying to find the inverse function's formula, okay? Step number one. Step number two, solve for x equals to stuff in y, all right? So you got some formula in y, isolate x, all right? And step number three is really not much of a step at all, but step number three is write f inverse of y is equal to that stuff in y. See, whatever you found up there, that's your inverse function. All right? Now, how many of you guys remember finding the inverse function in previous classes, right? Is this what you did?
Our teacher just taught us to switch x and y and just solve for y.
Ah, so this is my step 4. Swap y for x if needed. And then that will give you f inverse of x equals, stuff in x. So basically it's the same pattern, but replacing y with x. Now, the reason I teach to switch the x at the end rather than the start is because there are applications where it is important to use y as a variable and not x. Let me show you an example of that, because I think that'll make why I care about this come to life. So I think an interesting example for all of us, example 4, is how about if we let x equal degrees in Fahrenheit, and we let y equal degrees in Celsius, right? You guys know about this, Celsius versus Fahrenheit, right? So what's the formula? How do they relate? So we could say y equals to f of x is what? What is the formula? You do x minus 32, right? And then that has to be multiplied by 5 over 9. And the reason that that's the right formula, think about this, is x equals to 32 is freezing, right? In Fahrenheit. And in Celsius, it's 0, right? And that formula gives you 0 when you plug in 32. What's boiling in Fahrenheit? In Fahrenheit, boiling is 212 degrees. But in Celsius, as you know from your chemistry class or whatever, boiling is what? 100 degrees Celsius, right? That's pretty much why we have the Celsius scale set as it is, right? What happens if you plug 212 into this? If you plug 212 into this, you get 212 minus 32, which gives you 180. 180 over 9 gives you 20. 20 times 5 is 100, so you can check. This does check those 2 points. And 2 points fix a line, so that's the right formula. Of course, we could have just Googled this, fine. So now, this is a function of x, right? X has meaning degrees Fahrenheit. Find the inverse function. Can you do it? So, step number 1, I write y equals to 5/9 x minus 32. Yeah? Solve for x. How would you solve for x here? I multiply both sides by 9/5, yeah? So I get 9/5 y equals to x minus 32. Add 32 to both sides, we get x equals to what? I'm about to be very sad if I don't move the camera. Let's see here. There we go. So we get what? X equal to 32 plus what? 9/5 y. So this is the quote-unquote stuff in y I'm talking about in my template over here, right? And there you go. This is f inverse of y is equal to 32 plus 9/5 y. And I would argue here, you don't really want to, in some sense, you don't really want to use the same variable for degrees Fahrenheit and degrees Celsius, right? Because that would be confusing. You'd be like, well, x is equal to 100, but x is also equal to 212. Like, how does that work exactly, right? If we're going to reserve the meaning of x as being degrees Fahrenheit, I don't want to also say it's degrees Celsius. But the meaning of the domain for inverse function here is degrees Celsius, right? So in that sense, you find yourself in a place conceptually where you need different variables for different domains, right? And we try very hard to avoid that in this course because we don't want to confuse students because we always want to talk about functions of x, right? Well, there are reasons where that is too limited a viewpoint when you actually apply math to the real world, right? You sometimes need more than one letter. Now, if I wanted to graph, why would you want to graph both of these on the same axis? What would that accomplish for you? Well, see, if I wanted to graph this and that at the same time, then I probably want to take the next step. So there you go. That's the inverse function. We found it. So follow-up question: what temperature does degrees Celsius equal to the degrees Fahrenheit, Well, okay, so one way you could do that is you could plot both on the same graph, right? So let's see here. Yeah, you could set them equal to each other, exactly. Sure, but if we do that, then we better use x for both, you see? So yeah, if we set 5/9 times x minus 32 equal to 32 plus 9/5 x, that makes sense because we're looking for where degrees Fahrenheit equals degrees Celsius, right? So you can solve that, right? If we do that, well, fine. I wasn't planning on this. 5/9 x minus 9/5 x equals to 32 plus 5 over 9 times 32, which is, what have I done? So 25 minus 81, right? Over 45 x equals to 9 times 32 plus 5 times 32 over 9, which gives me x equals to minus 40. Okay. I'm actually not sure about that, but I remember the answer was minus 40. So it's just a random bit of trivia, but I think if we do the math here, hopefully we get it. I mean, golly, I'm burning valuable class time on this. No calculator either.
Remember, you need to go about like 8 minutes over.
Oh, I need to go 8 minutes over? Okay, well, thank you. Hey, that helps. Well, if you don't mind, let me just leave that as I think this is true. If I haven't made a mistake, the solution to that should be minus 40, yeah? What's more interesting, though, is to graph the function and the inverse function on the same picture, right? There's a reason, there's a place where if you want to study how the function looks like and how its inverse function looks like, and if you want to look at them on one graph both at the same time, that's when step 4 is also needed, because you need the formula for f inverse, right? So like here, if I wanted to look at the graph of both the y equals f of x, it has a 0 of 32, right? And it's got a slope of 5/9, right? So 5/9 is what? That's about 0.5, right? So the original conversion formula has a graph that looks kind of, sort of, something like this, all right? So there's y equals to f of x. What's the, if I change y to x here, right? If I write, y equals to f inverse of x equals to 32 plus 9/5 x, where does that go through 0? Can you figure out what the 0 is of that? So if you just set this equal to 0, what do you get? It gives me x equals to minus 32 over 9/5, which is like minus 160 over 9, which is what, like, man, I really wish I'd not left my calculator in the office today. It's negative anyway, and it's kind of sort of about like minus 10-ish. I don't know, it's somewhere in here, right? This is 32. So this one's more like here-ish maybe, right? There's a different slope, right? The slope of the inverse function is 9/5. So what's that graph look like? If I did it right. Yeah, if I had it right, it should be something like that. All right. So there's y equals f inverse of x. If I made the graph exactly right, the way it should look is they should be symmetrical around the line y equals x is what we're going to learn. When you graph a function and the inverse function, the pattern should be that they're sort of reflections of one another across the line y equals x. So if I put y equals x, it should run right down the middle of these guys, I believe. Where do they cross, though? Is that right? Do they have to? I'm sorry, they don't. Let me stop. Anyway, I'm pretty sure that this point of intersection here is, minus 40. But I happen to remember that. I haven't worked out the algebra at the moment. Okay, let's go on here. Let's try another example. Let's find the inverse function for my restricted function. So where am I? Example 5. So remember we had g of x equals to x squared plus 3, where x is greater than or equal to 0, right? Let's find the inverse function to this, okay? So what do? We set y equals x squared plus 3. All right? Solve for x. So isolate x squared is y minus 3, right? When we have something squared equals to whatever, the solution to that is x is equal to plus or minus the square root of whatever is there. So this gives me x is equal to plus or minus the square root of y minus 3. Right? I mean, algebra does that, but now look at the context here. What are we told at the start of this example? We're told x is what? Right, but x is greater than or equal to 0, so we choose the plus. We have to choose the plus because we forced x to be greater than or equal to 0. And as such, we get x equals to the square root of y minus 3, which tells me that f inverse of y is just the square root of y minus 3. So there you go. That's a formula for the inverse function. Now, suppose you want to graph the inverse function and the function both on the same axis. Then we should go to step 4, right? To graph both y equals f of x and y equals f inverse of x. F inverse of x is what? It's the square root of x minus 3, right? You guys with me? So to get the inverse function, we just swap y for x at the end. Now, some of you guys are like, well, I swap y at the beginning. Can I do that? Sure, you can do that if you want. But do try to follow the instructions for my problems, right? If on the test I say, find a formula for f inverse of y, then I want the formula with y in it, right? If I say find a formula for f inverse of x, then you want the formula to have x in it. All right. Now you guys writing x or y where you should have vice versa, the one or the other, that's not going to be like an 80% deduction or something. I'm talking about like 10% of the credit for that, all right? But it is something I want you to think about a little bit. It is really nothing terribly deep in what I'm saying at the moment, okay? So what's the graph of g look like? Let's take this as an opportunity to look at the graph of the function and its inverse function. The graph of g was half the parabola, right? So it started at 3, and right, it goes up something like this. Because we're only looking at the positive half of it, right? What's the graph of y equals the square root of x minus 3 look like? That's the square root graph, right? Shifted 3 to the right. So we can graph that. It's what? It's just the same, but like this. How about the comments I made about range and domain? Do you see that playing out here? What's the range of g? See how that works? Ow. That smarts. Range of g is 3 to infinity. Right? What's the domain of g inverse? 3 to infinity, right? What's the domain of g? By assumption, it was 0 to infinity, right? We put that on there. We forced that. Yeah? What's the range of g inverse? 0 to infinity, right? That's how this works. There's this interplay. The range of the function is the domain of the inverse function, and vice versa. This is actually kind of neat because what this means is that you can calculate the range of certain functions by just finding the formula for the inverse and finding the domain of the inverse function. That's a kind of sneaky trick. Let's try it for something a little bit interesting. So let's look at y equal to it was for a good cause. Let's see here. It's about time to wash this thing anyway. Example 6. So suppose you have f of x equal to x minus 1 over x plus 1. Let's find the inverse function for this one. All right, here we go. We write y equals to x minus 1 over x plus 1. Now we have to do what? We have to solve for x, right? Solve for x. So this gives us y times x plus 1 equal to x minus 1, multiplying x plus 1 to the other side. Now multiply it out. Multiply it out. We get yx plus y equal to x minus 1. Next thing I want to do is I want to isolate x. I want to bring all my x's to one side. So I got myself a yx minus x is equal to minus 1 minus y. All right. Factor x out, right? Factor x out. So I factor my x out, and I've got x times y minus 1 equals minus 1 minus y. All right. Now divide by y minus 1, we've got it. So x equals to minus 1 minus y over y minus 1. And there you have it. This is the formula for f inverse of y. F inverse of y is equal to minus 1 minus y over y minus 1. And if this is bothersome, aka f inverse of x is equal to minus 1 minus x over x minus 1 if you prefer writing the formula with x. There it is. Now my question to you is, what's the range of this function? So notice that the domain of f is what? What's the domain? Everything except for what? See what we can't put x equal to minus 1, right? So the domain is everything except for minus 1. All right? What's the range of this function? It's the domain of the inverse function, right? What's the domain of the inverse function? Look at this formula. What's the domain? Everything but 1. Now, how would you have found the range if not for this trick I just told you? How would you find the range for a function before this? What did we do? What did we do? We graphed it out. Now, can you graph this function? We can, right? So check it out. This is the graph of the function. I would like to point out we didn't have to graph it to find the range. I'm just showing you why the range is what we found it to be. Look at this. This has horizontal asymptote of 1, right? Degree 1 over degree 1. So it's got a horizontal asymptote of 1. And it's got a vertical asymptote at minus 1. It's got a x-intercept of 1. And it's got a y-intercept of minus 1. So the graph, we're a little bit short on time, so I'm just going to show you it. Looks like this. Usually I run through the sign chart and everything, but there it is. The range is what? Everything except for the horizontal asymptote, which is at 1. That's what we found looking at the domain of the inverse function. What would be... And what if you were to graph the inverse function? You could graph the inverse function on this graph as well. I'm not going to do that because we're out of time, and also because it's going to get really busy. And my graphs aren't quite accurate enough on the whiteboard to do it justice. So anyway, I shut up. Have a good weekend. Oh, and sorry I didn't